Hello, and welcome to Short Takes 331. Today, we are going to talk about linear systems of equations, and this is going to be a series of videos on this topic. So this is part one. And let's start with a simple example or two. So here you see a very simple system of linear equations. The first equation is simply x1 plus 3x2 equals 9, and the next one is x1 minus 7x2 equals 1. And here the unknowns are x1 and x2, and because they don't appear elevated to any power other than power 1, we say that these equations are linear. And similarly, here in the second example, we have x, y, and z as our unknowns, and we have some coefficients like 7, pi, I, the imaginary unit, 2 and 3, minus 2 and 3, and so on. And we have a right-hand side here, which is 0, 21, and 1. So this is written in a very conventional way, where all the unknowns appear to the left, and all there's some right-hand sides that don't depend on the unknowns at all. So this is one system, and here's another system. And this is what we call a 2x2 system, and this is what we call a 3x3 system, because there are here 2 equations and 2 unknowns, and here we have 3 equations and 3 unknowns. And usually the systems are addressed with matrices and vectors, and we saw that before, but as a reminder, you can write these systems using matrices and vectors in this way. For the first case, we define a matrix in this form: 1, 3, 1, minus 7, a vector of unknowns, x1, x2, and a vector of the right-hand side, b, encoding these numbers 9 and 1. And if you take this matrix and you multiply by this vector, you take from the first row and the column vector, you get the first equation. And for the second row and the vector equals 1, you get the second equation. So this is a very compact way then, if you want, to represent our big system of equations. And it really separates very nicely what is the information that is given to us, the matrix 1, 3, 1, minus 7, this matrix A, on the right-hand side, from the unknowns x1 and x2. And it's the same for the second system of equations, where we have 7, pi, minus I, and so on and so forth. These are all our coefficients. These are given to us. And then we have the unknowns x, y, and z, and our right-hand side, 0, 21, 1. And our job then is to solve for x. So we need to take this problem and we need to solve for the vector x. That is, we want to know all these unknowns, in this case, x, y, or z, or x1 and x2. Okay, so these are just 2 examples. So we may have more generally a matrix A made out of coefficients with m rows and n columns, taking values in some field, which could be the real numbers typically, although in a lot of the examples I've shown here it's just integers, but it doesn't have to be. It could be any field of real numbers or complex numbers even. X then will be a vector of size n, so n components, and b would be, there will be as many b's as m's as the number of rows in A, and so b would belong to some field then of numbers, and it would have m components. So, and we distinguish in 3 cases. You could have m greater than n, so more rows than columns, and what that means is that you have more equations than unknowns, and typically when that happens, there's no solution, unless there are some superfluous equations that you can remove, and so you don't have more constraints than unknowns. Then usually this would mean that there's more equations than unknowns. So you're over constraining the problem, and so typically there will be no solution, except in special situations where actually some of the equations that you have are not really constraining anything beyond some other equations that you all still have in your problem. And so then you remove the superfluous ones, and then you may find yourself actually in this situation where m is equal to n. You will have as many equations as unknowns, and so it's possible to have a unique solution. So you may have as many equations as unknowns. Each equation, if you want, manages to constrain one of the variables, and so you may have a unique solution. Now, if also in this case you have some superfluous equations, then it may be that once you remove those superfluous equations, I don't give you any extra information, and we'll see an example of that, you may find yourself in this situation where m is less than n. And so here you have fewer equations that are knowns, and then that means that you have an infinite number of solutions. And this simply is because your equations don't manage to constrain all your variables, and some of the variables will be left to have an arbitrary value, and we'll see an example of that. And that means that you have an infinite number of solutions. So this is basically the 3 cases that you can expect to have. The most interesting one is this m equals to n, when you really have no superfluous equations. You have as many equations as unknowns, and so it is possible that you may have a solution that is unique. And we'll talk about that and how that is related to the existence of the inverse of our matrix A. So if you find these videos helpful or useful in any way, please consider liking them and subscribing to the channel. This is a series of videos that are meant to help my students at UNC Chapel Hill. But if you're not a UNC student and you're looking for a tutor in math or physics, in English or in Spanish, feel free to contact me. You can do so at shorttakes331@gmail.com, or you can leave a message in the comment section below and I'll get back to you. So in the first case, where m is greater than n, here's an example. You may have more equations that are known. That's what this means, m greater than n. And so here are equations. They're specified by this matrix, 1, 3, 2, 4, 8, 9. And the equations basically tell us that 1x1 plus 3x2 has to be equal to -1. And so on and so forth, 2x1 plus 4x2 has to be equal to 0. And 8x1 plus 9x2 has to be equal to 2/3. For whatever reason. This is just a random example I came up with. And you will find that actually this set of equations is giving you too many constraints. There's no solution to this problem. There's no value of x1 and x2, no values of x1 and x2 that satisfy all these equations at the same time. Now, here's another example where we have the first two rows of the matrix are the same, and the first two rows of the right-hand side are the same, but the last equation I have changed it, and I inserted here 2, 6, and -2. And if you look carefully, you'll see that that is simply a multiple of the top equation. It's a multiple of 1, 3, -1. So it's 2, 6, -2. And so that really is just the first equation multiplied by 2. It doesn't add any new information. If you have a system that already manages to solve the first for the first equation, where 1x1 plus 3x2 is -1, then the last one is satisfied trivially already. It's just multiplying both sides by 2. And so this last equation is superfluous. We can get rid of it. And so if you do, then you end up with a system of two equations with two unknowns. And it's what we have in the next example here. You will have a case where m is equal to n. And in that case, you can go ahead and see, you can see that you can solve it right away. And here I'm doing this by writing the equations in full form. Later, we'll see examples where you can do this just you're working with matrices directly. But here then is our explicitly written our two equations. x1 plus 3x2 is -1. That's our first equation coming from this matrix multiplication equal to -1. And then we have 2x1 plus 4x2 equal to 0. This is nice, equal to 0. We take this last equation and solve for x1 in terms of x2, and we take this -2x2, we put it up here, and we solve for x2 in turn, and we find as a result of that, using these two equations, that x2 is -1, x1 is 2, and there's nothing else. That's it. We just executed a couple of logical steps, mathematical steps that have no ambiguity, and so this is a unique solution, and that's it. That's a solution to our problem. So you see that this system of equations actually has a unique solution, because in reality it was this one hidden in the background. This last equation doesn't give us anything new, but if we had to solve this equation up here, then this would be completely different. There would be no solution in that case to the three equations with two unknowns. But here we do have this. Now if we have a situation where m is less than n, we have fewer equations than unknowns. And so imagine that we take this system and remove the last equation entirely from the problem. Then we are left with 1, 3, x1, x2 equals to -1. And that takes this form then in terms of equations, x1. So 1x1 plus 3x2 equals to -1. That's our one equation. You can solve for x2. All you want is x2 equals -1 minus x1, everything divided by 3. And that's it. There's nothing left. So x1 can be anything. Once you fix x1, you get x2. And you're done. So x1 can be anything, could be any complex number, any real number, wherever you want. Then you calculate x2 in this way, and you have an infinite number of possible solutions as a result, because x1 can be anything. So you see, this is what we mean when we say that when m is less than n, you will have an infinite number of possible solutions. And that's why this case, m equals to n, is more interesting, because then you may have then a solution that is unique. Typically, what will happen in cases where the solution is not unique is that, again, you have some equations that are giving you information that you already had. So you have superfluous equations, and so it looks like you have m equals to n, but in reality, you have this case m less than n. And we will continue to talk about that in future videos. Now, in all of the above, in all this discussion that we talked about so far, we assume that the vector b, the right-hand side, is non-zero. And this is what gives us what we call an inhomogeneous systems of equations. These are the most interesting ones, the inhomogeneous systems of equations. And they're the most interesting ones because it turns out that if b is equal to 0, then there's always a solution. You can always solve the problems if b is equal to 0. And you just have to set x equal to 0, because every time you multiply a matrix by a vector, if you set that vector to 0, no matter what a is, if you put x equal to 0, you automatically get 0 as a result. The 0 should have a vector on top here, so it's a 0 vector. And so this is then what we call a homogeneous system of equations, and it can always be solved by just setting x equal to 0. Now you can ask, is x equal to 0 the only solution? And we'll get back to that. And again, it is related to whether the matrix A can be inverted or not. If it can, then you can put A on the other side of the equation, and you will get that matrix with multiplied by 0, which gives you 0, and you will have that indeed the only solution is the solution that we already know about, which is that x is x equal to 0. So again, we have inhomogeneous systems of equations in the discussion we had before, and here for the homogeneous systems of equations, we always have the solution x equal to 0. So here are some examples where m is greater than n, so we have more equations than unknowns, where we say in general there's no solution for an arbitrary right-hand side, but if a right-hand side is just 0, 0, 0, like you see here, is all zeros, then you see that clearly x1 equals x2 equals 0 is a solution. So you can multiply any of these rows by this column. If you put this column to 0, you will get 0 as a result, and so that always works. Are there other solutions you can ask other than that x1 equals to 2 equals to 0? So here, if you write down these equations, you'll see that x1 plus 3x2 equals 0 tells you what x1 has to be in terms of x2. You can insert that into the second equation, and you'll find that you have to have that both x1 and x2 is equal to 0. If you follow the line of reasoning here, you see that it must be that x2 is 0, which sets x1 equal to 0, and so there's nothing else. There's nothing else to do here. Now, in another case where you may have only one equation here, or rather if you want fewer equations than unknowns, so here's one equation and two unknowns, then you have 1x1 plus 3x2 equal to 0. That sets x1 equals to minus 3x2. And other than that, you can set x2 to whatever you want, and it will determine x1, and that's it. That will solve the problem. And so we have a lot of solutions other than 0, 0, as long as they take this form. For example, you can set x2 to 1. That means that x1 is minus 3, and that is also a solution to this problem. And this is then an underdetermined system of equations. So we have an infinite number of solutions. There's infinitely many solutions to this problem. And finally, here's the 3 by 3 case where I wrote down this matrix, which is a bit of an enlarged version of the previous problem. So it's 1, 3, 2, minus 2, minus 6, minus 4, and 1, 0, 0, and x1, x2, and x3 are the variables. They are the things we want to solve for. And you see right away that this row here and this other row, the second row, they're related to each other very simply. The second row, if you want, is minus 2 times the first row. So you see this is minus 2 times 1, this minus 6 is minus 2 times 3, and this minus 4 is, of course, minus 2 times 2. And so this row is not really giving us any new information. And how does that manifest itself in the solution? We will have an infinite number of solutions, once again, because we will have fewer equations that are knowns in reality. So let's look at this equation, for example, the one coming from 1, 0, 0. If you take this equation and multiply by this vector, you will get simply that x1 has to be 0. This equation right away is very simple. This row is telling you that 1x1 plus 0 and 0, x1 and x3. So we only get x1 out of this equation equal to 0. So that's what we have here. x1 equals 0, whereas if you take the first row, for example, you get that x1 plus 3x2 plus 2x3 has to be equal to 0. That's multiplying this guy by this guy. You get 0, and that just tells us that by setting x1 equal to 0, because we learned that from this one, that there's a relationship between x2 and x3. So and x3 are related by this. But other than that, that's all we have. We don't know anything else because, again, this last equation doesn't give us anything new. You can do the multiplication. You can convince yourself that this second equation gives you the same type of relationship between x2 and x3. And so you can say, well, okay, my solution must have x1 equal to 0. it must be that then x2 is related to x3 in this way. But other than that, you could set, for example, x3 to whatever you want. If you set x3 to 0, you get 0 here, but you can set x3 to 1, and then it will give you that x2 is 2/3. And that's also a solution to this problem, okay? So not only do you have the 0, 0, 0 solution, which you always have for homogeneous systems of equations, but you also have other solutions. And in this case, you'll see that you have an infinite number of solutions. That's all I have for you for this first part of linear systems of equations. If you enjoyed this video, please consider liking and subscribing. And this is a series of videos for my students at UNC, but if you're not a UNC student and you need tutoring in physics or math, in English or in Spanish, you can contact me. You can do so at shorttext331@gmail.com, or you can leave a comment in the comment section below. That's all I have for you. I look forward to seeing you in the next video.